Hello everyone, today I will be presenting my EE474 project, and it's the measurement of the main field in homogeneity for the 3 Tesla Siemens scanner. So as we all know, for every MRI scanner, there is a main polarizing magnetic field that aligns the magnetic spins within an object. Ideally, this field should be as homogeneous as possible so that all the spins are precessing at the resonant frequency. However, most of the times in practice, we face off resonance. Some of the reasons are the main field inhomogeneity, the susceptibility-induced field variations, and the chemical shift. These sources can lead to artifacts in the images. It could be the signal intensity loss in some parts of the image. It could be distortions and blurring or curved slice profiles. So in order to correct for these inhomogeneities, we need to quantify them first. Uh, by making use of the phase information, we can quantify the inhomogeneity. If we manage to acquire 2 scans at least with different echo times, we can actually calculate the field inhomogeneity as it's the ratio of the phase difference to the gyromagnetic ratio multiplied by the difference in echo time. So, in order to construct the field map of the inhomogeneity, I had to choose an appropriate pulse sequence. I choose the gradient echo because of 2 reasons. Well, the gradient echo is constructed by a single RF pulse with a gradient reversal. The single RF pulse makes the acquisition faster and it reduces the scan time. And the gradient reversal does not affect the phase shift, so the field inhomogeneity can be detected. Um, for the acquisitions of the GRE, I acquired 3 separate scans using a label GRE at 3 different echo times, 5 milliseconds, 12 milliseconds, and 20 milliseconds. Some of the other parameters in the sequence were the repetition time, 100 milliseconds, flip angle was 10 degrees, and the resolution was 256 by 256. Um, After doing the scans, I acquired the data using a 3T2 channel coil in order to increase the signal-to-noise ratio. The magnitude images were constructed by using a sum of squares method, and the phase images were averaged, but the phase was wrapped between minus pi and pi. And the solution to that was to work with the phase difference between the echo times, but this solution did not eliminate the problem entirely. So for the phase unwrapping, unfortunately, the MATLAB built-in functionality does not support 2D unwrapping. So I had to find an algorithm. Um, the algorithm used was based on sorting by reliability, and it was robust. It could handle the phase discontinuities. Also, it was efficient. It has 0.5 seconds for processing the images. It's also effective. It could handle the noisy data. To generate the B0 field map, I followed 3 simple steps. First of all, I had to estimate the phase evolution between 2 echoes. And I did that by taking the Hermitian inner product of the complex signals at different echoes. Then I used the weighting factor to construct the field map, which was the weighting factor was the ratio of the absolute value of the complex signal, the, the evolution of the complex signal of the kth echo to the first echo. And finally, the B0 field map was constructed by relating the difference in echo time, the phase evolution, and the weighting factor. Moving on to results, here you can see the magnitude images for each acquisition for 5 milliseconds, 12 milliseconds, and 20 milliseconds. You can, here it's hard to differentiate the difference of the echo time because it's not reflected much on the magnitude images. However, when we look at the phase images, they look more different than the magnitude images because the difference in echo time is reflected directly on them. Here I constructed the phase maps between the different echoes. On the left, you can see the phase map between the first echo and the second, and here you can see the difference between the first echo and the third echo. And finally, I generated the B0 field map. You can see it here after masking it. So the B0 is 3 Tesla for the Siemens scanner, and the inhomogeneities were ranging between -5 to 2 microteslas. So when converting that to parts per million, it's -1.5 to 0.5. And then to understand the importance of the unwrapping procedure, I took a look at the phase map in the wrapped case versus the unwrapped case. In the wrapped case, you can see here that the background is very noisy and the phase is very discontinuous. But after doing the unwrapping, uh, the background is way less noisy and the phase looks more continuous. Some ways to improve my measurement were to acquire the phase maps directly from the scanner, because the scanner reconstruction algorithm is way better than the reconstruction I use myself. Also, I could have used the FSL toolbox to unwrap the phase. Also, the optimized choice of echo times to eliminate the wrapping of the phase. And finally, incorporating the coil sensitivity in the reconstruction would have increased the reliability of my measurement. And these are my references. Thank you for listening.